We did the pulley was a disc last time, correct? And it could be any round object ultimately could be used as a pulley if you can affix it correctly to your device. However, what I want to talk about today is a different example, are composite objects, where you composite an object together. So what I have here are a ring, mass M, radius, radius D, and I have a bar, mass also M, but length 2D. So I'm not trying to trick you. This is our radius of the bar is D, but the ring has a radius of D, but the bar has a length of twice the radius, so the bar is one diameter. Does that make sense? You guys following along with what I'm trying to indicate? Because each of these two objects has its own independent moment of inertia. We know that the bar is 1/12 ml squared about its center. That's the moment of inertia of a bar. And a ring is mr squared, as long as it's being rotated about its center. But what we're going to do is we're going to create a composite object. We're going to take the bar and use it as a spoke for the ring. The idea being here is that we could use this as a rotating pulley. So what I'd like you to do is, in terms of M and D, I want you to calculate the moment of inertia of this composite object. And it's not particularly hard, and I'm going to show you how it's done, but moments of inertia add together. So we have two separate objects. We have the moment of inertia of the ring and the moment of inertia of the bar. Now again, there's the base moments of inertia. I mean, there's the equations that we have for each object and its moment of inertia. And we've already talked a little bit about some of them, but a ring is mr squared, where m is the mass and r is the radius. But we have the radius is d, so we would write this as md squared. That would be its moment of inertia in the terms given to us. Now, a bar is 1/12 ml squared if you're rotating about its center, but we're not going to use L because we were told that the length of the bar is 2D. So one of the first changes is, we have to use the variables they give us, but we still have formulas for moments of inertia. So we have to remember what the formula is about and how to use the information they've given us in those formulas. So just again, I'll write this off to the side. A ring is defined as mr squared, and a bar about its center is 1/12 ml squared. So we are using those formulas to come up with what the moment of inertia is in the terms they've given us. Now, there's not a whole lot here. I mean, this is just going to be md squared, and when I square the two, I'll have 4/12. So when I add these together, I'll have md squared plus 4/12 md squared. Thank you. The idea here is that we should have a moment of inertia at the end that's all in the same units. Now, 4/12, I think you guys know, is 1/3. That's not a huge stretch, I hope. And when I add these together, I'll get 4/3 md squared, right? Common denominators, NAD. And this is the moment of inertia of our pulley. It is a composite object. Any questions about what I mean by a composite object now? So it is really common for them to have a composite object like this. They want to see if you understand that you can combine moments of inertia of individual objects into a single object. So for the most part, it'll be nothing more than this complicated. But imagine it with maybe 4 spokes or 6 spokes, something like that. It's not much different. You'll just have multiple bars. If there's 2 of them to make 4 spokes, you just multiply this by 2. It's not a huge deal, but it's something to keep in mind. They're going to probably, the test writers, they can do little things like that. Don't be thrown off. Moments of inertia add together. All right? So now let's talk about the problem we're going to do with this. Imagine we hang this from the ceiling using some kind of connector so that it is able to spin freely about its center, and that we hang on either side two different boxes. M and 3M. Okay. I'd like you to find the acceleration of one of the boxes. Now this is a repeat of what we did on Friday with a little bit more complicated stuff, but not much. So I'm looking for an expression for the acceleration of one of the boxes. I want the linear acceleration. Now, a couple things. I'd like you to start by doing the same kind of thing we did before, which is to start with free body diagrams for each of the objects. But just remember, this tension and this tension are not the same. We're going to ask some questions about that when we get started, okay? Or I'm sorry, after you guys get started. So take a minute and please set up the problem in the same way we set it up on Friday with our free body diagrams and our net force equation. And let's just make sure we're all in agreement. I think it's going to rotate this direction. So I want that to be the common direction for positive for all of us. All righty? All right, take a second. All right, so lots of good stuff. Are some little things here. So as I walk around, I saw a few different things, and a few common mistakes, though. One of them is I would focus, if I were you, on the force part first to kind of identify what's happening. So we know that the weight on the left side has to be greater than the tension on the left side, because I'm pretty sure we can all agree this is going to be accelerated downwards. It's bigger. Similarly, on this side, I'm expecting the upward tension here to be greater than the weight on this side, because I'm pretty sure that that box is going to be accelerated upwards. But these two aren't the same either, because there needs to be an unbalanced torque to cause the wheel to rotate. But this is the first part, and this generates 2 relationships, one for each box. So I'm going to make this positive here and this positive here and fill out a couple of force equations. So for this one, I'll have 3mg minus TL, and I'm just using L and R because it's left side and right side. And then this equals 3ma. On the other side, I'm going to have TR minus mg equals ma. Just little stuff. Remember, this has to match the mass of this box, and this has to match the mass of this box. So little things to keep in mind. But that's as far as we can get here. A few of you had other stuff here for this, listing other forces, but we don't know what's here yet. We don't know the size of these two forces. We do know that those two forces act on the pulley. So the pulley is experiencing TL on the left side and TR on the right side. Those are acting directly on the pulley. So the pulley is experiencing a net force of 0 because the pulley doesn't go anywhere. So there's lots of forces acting on the pulley that we haven't identified, like it's got weight and there's a normal force. I mean, these forces are all acting on the pulley, but the only ones that actually matter are going to be the ones that act outside the center of mass, because these cause it to rotate. And those are the ones that we're interested in. So that'll be net torque equals I alpha. Now, I need you guys to really look at the torque one. I can't do this one for you right away. I need you guys to kind of bang this around a little bit. So remember, a torque is R times F times the sine of the angle. Look at what we did last week to kind of come up with what this one looks like, because this one is kind of the critical one. And I'll remind you of some stuff that we have to kind of work out here. Is you're going to be putting in your moment of inertia. You're going to be substituting A over R here, but you'll need to figure out what R represents and do the substitution correctly. And of course, figuring out what each of the two tensions are. Be careful there. I saw a lot of people being a little bit, sloppy is the wrong word, not paying attention to what an R means. There's lots of different R's here. So be paying attention to that. All right, I'll give you a few. All right, so just want to walk through this a little bit because I think there's a few of you who need it. How many torques are acting on the pulley? 2. So there's a torque on the left and a torque on the right. I'm going to make the one on the right the negative torque and the one on the left the positive torque, because that's the direction that I've indicated as positive and negative already. So as I look at these, the torque on the left is going to be from this force, this tension, and it's acting a distance d from the center. So not a capital R, not a lowercase r. We have to use the variables that are in place in this problem, and d is the variable to use here because that was the radius of the ring. So this will be d times TL. And I don't have to worry about the sign here because we know that for any pulley, the angle is going to always be 90 degrees from the radius. So it's always going to be sine 90. So I just leave that out if it's a pulley. And that suggests that this is going to be d times t for the right. We're going to add those together and get dTL minus dTR equals, now I need I, the moment of inertia. We calculated that already. It's right here, 4/3 md squared. And now we need this substitution to put it in terms of the linear acceleration, not the angular acceleration. But again, not r. R represents the radius in this problem, which is still d. So that's going to be A over D. I know it's a lot. That's why we're being nice and slow. So if you didn't get this, before I go any further, put something in your notes to help you the next time. So where did this come from? Where did this come from? And where did this come from? And I'll remind you, this is the condition for rolling that we're basing this on. The string rolls around the outside of that pulley. This is the moment of inertia. And this is the sum of our torques. But you should also write notes about where we came up with each one of those. Something so that the next time you've got something to help you. Let's get this in focus here. I've got a d in this term and a d in this term. So we can factor those out. And cancel one of those with one of those. And then we have one right here and one right here, so we can cancel that other one out too. So the d's cancel in this case. And they often will. Often the radius will cancel out when you're working problems like this. It's kind of by design. But still look for it. Make sure the math is right. But when we do that, that allows us to take these three things that we have now and kind of pull them together. We've got this force relationship, and now this thing, which is going to be TL minus TR equals 4/3 MA. When you're done, you should get one force equation for each object that has inertia. And so we have three objects with inertia. I have three equations here. And these three equations have internal forces with them. Now, you might be asked to find those forces later, but the best way to do so is by finding an expression for the acceleration now. So that's what we're going to do. We're going to find an expression for the acceleration first. And that involves just adding these three things together. When we do, the TL will cancel with this TL, right? Got one positive and one negative. The TR will cancel with this TR, because again, one positive and one negative. And I'm left with 3mg minus mg on the left side. This is the net force. These are the two unbalanced forces that are acting on the pulley. They're hung on either side of the pulley. Now, the right side, we're just going to add everything together. I'm going to factor out the MA, though, and I'll get M plus 3M. I guess I'm just going to factor out the A plus 4/3 M all times A. I leave it like this for at least this step to show you guys that you should have anything that had inertia in the problem should show up here. And its inertia should be here. This 4/3 comes directly from the moment of inertia of the pulley that we found ourselves. This 3 is the mass of the box, and this is the mass of the other box. It's going to add all those together. And I did common denominators, and this got me 16/3 MA, and this side was just 2 mg. And we're nearly done. There's not much to do now. Just cancel out the m, solve for a. And I found that a is equal to 6/16, but that's 3/8. So 3/8 g. Any questions yet? Because we stopped here last time. We found just the acceleration. But there's a number of other questions that can be asked of you. So as we look at what's possible on both an exam or on a test, here are the possible other questions. So the first question here is, what was the acceleration? But they could ask, what was the pulley's acceleration? That would be finding alpha, not A. Not hard, but again, it's a different question. And then probably the most likely is, what were the tensions? These are the most likely follow-up questions for a problem like this. So I thought we would walk through each of these follow-up questions to see how they're done. Let's start with the one I think is probably the easiest to do. That's finding alpha. It's going to be very straightforward because we have a relationship already that brings those things together. So alpha is equal to A over R. Right? We substituted that in earlier. This would just have us figure it out now that we know what A is. So in this problem specifically, you would have to put in what we know R to be. And this would be lowercase d. That was what our radius was. So for this one, if we were supposed to be figuring out what is alpha, alpha would be our acceleration, 3/8 g, divided by the radius, which in this case was lowercase d. Now, I probably wouldn't leave it looking like that because that's pretty hideous. I would probably write this as 3g, whoops, that's a q, 3g over 8d. Good so far? Keep going? Because the next thing is what are the tensions, and we had two of them. Now, if you look back up at your notes, you probably have lots of places where you can see TRs and TLs. But there's probably one that's right to use and one that I wouldn't use. So if I wanted TL, I would probably use this relationship. And if I wanted TR, I'd probably use this relationship. I'm not saying it's going to be easy, but that's what we're going to do. So let's start with TL. So I wrote the relationship down. 3/8 g. So I'd put 3mg minus the tension equals 3m times 3/8 g. Do you see what we're doing here? And it's just algebra, but it's messy. It's a lot. So I want to get TL by itself. I'm going to go ahead and first, and I'll combine all of this into something better. 3 times 3 is 9. So 9/8 mg. Subtract it from the other side, while at the same time adding TL to the other side. Can you guys do that all in one step? Is that something you guys can do in a single step like that? I don't know how you guys are with the algebra. I'd get common denominators again, but you can work in decimals if you feel better about it. But I'm not particularly scared of fractions, so I'd probably just make this 24/8 and subtract. And 24 minus 9 is 15. So 15/8 mg. Now, how about you guys do TR? Does that make that's a reasonable exchange? Okay. You guys about done? Need a few more seconds? Okay. for us to kind of talk there. I got 11/8 mg. Is that what you guys got? Anybody need me to do this? Okay. So, a couple things that you could look for. TL had to be greater than TR. Did it work out that way? These are the little things we're trying to look for to make sure our answer is right, but also the things we have to pay attention to. So we know that these two things have to be, they're related, but it's important to know that we knew going in TL was greater than TR, and that's what we figured out here. But also, TL had to be less than 3 mg, and it is. And TR had to be greater than mg, and it is, right? Because TR lifted the one weight, but the other tension wasn't great enough to lift the other weight. That's why it accelerated downwards. So all of those things have to work out here. But I'd argue this is a lot. Wouldn't you agree? Starting from compositing a moment of inertia down to figuring. One more thing from this problem we will have to discuss, but we don't have time. But it has to do with how this thing is mounted together.